Hello all. Even though the exam season is over, as I mentioned, I'm trying various different ideas about new types of content I can have in my channel. And some of that content is not going to be exam or A-level related, but okay, that's another story. So for today, I'm going to go over yet another past paper, but for the first time, we are going to do OCR, okay? So my understanding is that this is taken by students in England, okay? And this specific paper is called Modeling Physics. It's A-level Physics A, and from what I saw, there is a Physics B as well. So there are many, many papers to be explored. I don't know how many of these I'm gonna keep uploading. We will see, but it's kind of fun, and I enjoy the interaction with students here. So anyway, I'm not gonna say too many things because this is literally the first paper I went over that is related to OCR. So far, I have been doing only at Excel. So just some general things. I mean, timing. So this paper has 100 marks, and you have 2 hours and 15 minutes, which is 135 minutes, right? So this paper should take you, I mean, for this paper, if a question awards about 10 marks, it should take you about 10, 12 minutes, something like that. Try to time yourself so you score as many points as possible, as many marks, excuse me. And the other general thing, of course, read the questions very carefully, make sure you understand what they're asking. Half the answer is in the question, as I say, okay? And the other thing is solve the problems that you are comfortable with first, build momentum and confidence, and come back to solve problems that give you hard time. Okay, don't overthink problems that you don't know how to solve, and don't waste your time because there is not enough time when you're actually taking an exam. So let's dive in. So section A is multiple choice section. And it says, by the way, I didn't see this. It says you should spend a maximum of 30 minutes on this section. So you see you have, I think it's 15 questions. So you should spend about 2 minutes per question, I guess. I don't know if they actually time this during the exam. So let me know in the comments. So let's start. Which row of the table shows two equivalent physical quantities? A is tempting, but 0 degrees Celsius is actually plus 273 Kelvin, so no. The second one, you have kilograms times meters per second, which is momentum, and then you have newtons times seconds, which is the same unit because you have kilograms meters per second squared times seconds, so you get the same unit as the first column, but 1 and 1000 are not equivalent, so B is wrong. Then again, 10,000 watts is okay. First of all, the problem with part C is that you have watts in the left column, and in the right column you have newtons times meters, which is joules, so that's wrong. So this is the only one left, which is correct. Okay, so we would select D, and it's correct because 1 millipascal is 1 times 10 to the negative 3 newtons per meter squared, which can also be written as 0.01 newtons per meter squared. Okay, so with multiple choice, try to also eliminate the wrong answers. Sometimes you can just arrive at the correct answer by eliminating all the wrong answers. Okay, let's move on. 2. What are the SI base units of the Boltzmann constant K? Okay, the Boltzmann constant K is 1.38 times 10 to the negative 23 joules per Kelvin. We don't care about the numerical factor, so it's joules per Kelvin, and it's A, right? No, that's wrong because they tell us base units. Okay, so we have to decompose these joules over Kelvin's expression. So 1 joule is 1 kilograms times meter squared over second squared, and then we divide by Kelvin, and then we see that the actual answer is C. Okay, how do I know that joules are kilograms times meter squares over second squared? Because the kinetic energy is 1/2 mv squared. So when we deal with units, we don't care about this factor of 1/2. So the units are kilograms meter squared over second squared, which happens to be the joule. Okay, so let's move on. Part 3. A rubber bung is attached to a string. Okay, the bung is whirled around in a horizontal circle of radius r. The rotational period of the bung is t. The tension in the string is kept constant as the bung is whirled around at different speeds. Which relationship is correct for this whirling bung? So this gave me hard trouble, and I will tell you why in a moment. But okay, so this is the bung, I guess. Okay, so something like that, and this is the radius, and it goes around in a circular motion because we hold a string that exerts a tension T. Okay, so let's call it tension or Tn just to avoid confusion with the period T. Okay, so this tension provides the centripetal force needed, right, to have circular motion, so that's equal to m omega squared times r. Okay, so tension can also be written as m times 4 pi squared over the period squared times r, because omega is 2 pi over the period. Okay, so we have to solve for the period. So t squared is 4 pi squared times the mass over the tension times the radius. Okay, so now let's go read. A is wrong because T is not proportional to R. In fact, T is proportional to R to the 1/2. Okay, now B is correct. Okay, because T squared is proportional to R. It's exactly what we wrote down here, right? Then C, T is proportional to R squared. That's wrong. And then D is also correct because T is proportional to the square root of R. So the answers are B and D. I was surprised that there were two correct answers. I don't know why this was the case in this paper. Let me know in the comments what's going on. So I don't know, but both are correct. So let's move on. 4. To determine the acceleration of free fall g, a ball is dropped from rest from a point vertically above a light gate. The ball has a diameter of 5 centimeters. It is dropped at time t equals 0. The light gate output shows that the ball passes through the gate between times t equals to 0.1 seconds and t equals to 0.14 seconds. The graph shows the output from the light gate, which shows exactly that, this dip in the signal because the ball passes through the light gate. Okay, air resistance has negligible effects on the motion of the ball. What is the value of g in meters per second squared from these measurements? Okay, so the first step is to find the velocity. Okay, so the velocity, which I will call average velocity, and you will see why in a moment, okay, is equal to the diameter, 0.05 meters, over the time it took to pass through the gate, which is this interval here, 0.04 seconds, and 5 centimeters is the diameter, right? So we get 1.25 meters per second. Okay. Now we have a new problem. So, this is the average speed as the ball crosses the gate. Okay, so this means that the ball keeps accelerating as it falls, right? So when it enters the light gate, its velocity is less than 1.25 meters per second, and when it exits, it's more than 1.25 meters per second. So this average velocity is the instantaneous speed at the midpoint, okay, if that makes sense. So I hope it makes sense. Maybe I should write it down. So I'm gonna write it down. So V average is the instantaneous speed when the ball passes through the midpoint, okay? And this midpoint, so T midpoint, is the average between the two times that they give us. So 0.10 plus 0.14 over 2, which is 0.12 seconds, okay? So now G can be calculated using the instantaneous speed, which is also the average speed. So actually, let me write V average so I don't confuse you. So V average over this time at the midpoint, okay? So 1.25 over 0.12, which yields 10.4 meters per second, which is C, okay? Okay, 5 was a problem I've never encountered before in my life, so it was fun thinking about it, okay? So a block of wood is floating in calm water, okay? The density of the wood is 700 kilograms per cubic meter, and the density of water is 1000 kilograms per cubic meter. What percentage of the volume of the block is above the water line? So the upthrust, I mean, if you have this block, okay, so this is the water and you have a block of wood that it's partially submerged, right? And partially above water, okay? So you will have two forces, the weight, M times G, and the upthrust from the water, right? So these two forces are gonna be equal if it's floating, right? So upthrust is mass times G. Okay, now what is this upthrust? Upthrust is going to be equal to the density of the water, right, times the submerged volume. So this one, the green one, okay, so V submerged, right, times G, okay. And now what is the mass of the block? The mass of the block is equal to the density of the block, right, times the volume of the block, times G, okay? So G can be cancelled. And we immediately see, I'm going to use a clean page. So we immediately see, so we move from there to there. So we see that the submerged volume, right, over the volume of the box, the total volume, is equal to the density of the box over the density of water, okay? So this is 700 over 1000, so 70%, right? So 0.7 or 70%, right? Is below water, okay? We're not done yet. Is below water. I hope this makes sense, okay? Because the displaced, again, the whole trick here is that the displaced volume of water is equal to the submerged volume of the box, okay? So what is above water? So 100% minus 70%, which is equal to 30%, is the percentage above water, okay? And that's our answer. So that's option C. Okay, another nice problem was problem 6. So you have a horizontal uniform beam of length 4L and weight W supported at both ends. An object weighing 2 times weight, 2 times W, is placed on the beam at a distance L from one end. Okay. What are the magnitudes of the normal reactions N1 and N2 on the supports at the ends of the beam? Okay, so basically this is a problem where we have to take moments. So before we do that, don't forget, because I did forget when I was solving it, I have to admit. So don't forget to add the weight of the beam at the center, at its center of mass, and the center of mass of a uniform beam of length 4L is at 2L. Okay, I hope this makes sense. And we will take moments about this pivot point P. Okay, so before we take moments, what kind of moments do we have here? We have an anti-clockwise moment from N2 and another anti-clockwise moment from the weight of the center of mass, right? And wait, yes, okay. And then we have a clockwise moment from N1. Okay, so we have to balance the forces and the moments. So for the forces, we have just N1 plus N2 must equal 3W, right? 2W plus W is 3W. And then we take moments about P, so we have N1 times 3L plus, oh, sorry, that's the only, excuse me. Okay, so N1 times 3L is the only clockwise moment, okay? And this should be equal to the anti-clockwise moments, so N2 times L, okay, plus W times L, okay? So this L cancels, and let's work this out. We have, uh, since let me think, we can solve the second equation for N2. So N2 is N1 minus W, and then plug into the first equation. So N1 plus N1 minus W is 4W. So we find that, let me think, wait, I messed up something. Sorry, N2 is 3N1 minus W, excuse me, so plus 3N1, okay? So we have, and this should be equal to 3W. What am I doing? This should be equal to 3W. Forgive me, guys. So we have N1 equals to W, pretty much, okay? Therefore, N2 is 3N1 minus W, so 2W, okay? And the answer is B. Yeah, you see, I got confused. So it can happen to the best of us. I'm not claiming to be the best of us. So anyway, so let's move on to question 7. Okay, the graph shows a velocity time graph for a vehicle. At time t equals to 0, the driver observes an obstruction in the road. A short time later, the brakes are applied and the vehicle stops. The braking force remains constant. The situation is then repeated. This time the vehicle starts with twice the original velocity. All other variables remain the same. Which diagram shows the correct velocity time graph for this new situation? The same scales are used on all graphs. Okay, so since the velocity is twice the initial velocity, all graphs are fine in terms of that. Okay, then the reaction time is the same, right? So immediately eliminate options C and B, okay, because you see that only A and D work, okay? And then we need the slope to be the same because the braking force is the same. So the deceleration is the same, okay? So the only one that works is A, okay? I hope this makes sense because the gradient here is equal to the deceleration, and we can count it as, let's call that 2, and let's call this 1, okay? So 2 squares of velocity and 1 square of time, okay? So only option A works because the gradient for A is 4 squares for velocity and then 2 squares. So you see it's 4 and then over 2. So 4 over 2 is 2. So only A works. I hope this makes sense. Let's move on. 8. The bob of a pendulum is displaced slightly so that the string forms a small angle theta which is less than 10 degrees with the vertical. The tension in the string is T. The small angle approximation applies. Okay. Which of the following pairs of quantities would give approximately within two significant figures the same value for the horizontal component of T? Let me think. First of all, if theta is small, okay, sine theta is approximately equal to the tangent of theta, and cosine of theta is approximately 1, okay? So the only one that works from these combinations that they show us here is C, okay? Because T sine theta and T tangent of theta are the same thing if theta is really small. Whereas option A, we have T cosine theta, which evaluates to T, right? Whereas T sine theta evaluates, and I forgot to mention that this is also equal to theta, but in radians, okay? So in the small angle approximation, this applies. Okay, so the only option that works is 3, because all the other options give you components that have a totally different magnitude. Okay, so that doesn't work. Okay, let's move on to question number 9. A mass suspended from a spring is pulled down 0.05 meters from the equilibrium point and released. It oscillates in simple harmonic motion. The frequency of the motion is 2 Hz. At time t equal to 0, the mass passes through the equilibrium point. What is the displacement in meters from the equilibrium point at time t? So, first of all, we need to find the period. So the period is 1 over the frequency, so 1 over 2 seconds. Okay, so at t equal to 0, x is equal to 0. So we need a sine function, okay? So need a sine function since sine of 0 is 0, okay? But omega is 2 pi times the frequency, which is actually 4 pi. So the only option that works is D, okay? Because the displacement is 0.05 meters. So at time t equal to 0, the displacement is 0, so that works. And then we have the correct omega, okay? I don't know why we calculated the frequency. I think we don't need it after all, so I'm sorry I did that. Okay, let's move on to 10. The natural frequency of an oscillator vibrating in air is 20 Hz. Which statement is correct about this oscillator? So the natural period of the vibrating oscillator is 5 milliseconds, which is not, okay, because it's 1 over 20, which is 0.2, right, seconds, so no. B, the oscillator can be forced to vibrate at maximum amplitude at the frequency of about 20 Hz. That's actually correct, okay, so B is the correct answer. Then C says the oscillator can be made to resonate at the frequency of about 40 Hz. Wrong. And then D, the period of the freely vibrating oscillator gets smaller as its amplitude decreases. They didn't mention anything about damped oscillation, so no. 11, a car drives over a bridge at speed v. The path of the car is part of a vertical circle of radius r. The mass of the driver is m. At the top of the bridge, the driver of the car experiences apparent weightlessness and no normal contact force from the car seat. The acceleration of free fall is g. Which statement is correct? So the situation is like this. So, okay, it's exaggerated, but let's assume that we have a car at the top of this bridge and we have a radius r, right? So what are the forces on the car? The normal force from the ground and the weight. Okay, so m times g minus n provide the centripetal force, which is mv squared over r, but n is 0, right? So we have m times g is equal to, oops, yes, no, that's correct, mv squared over r. So I'm gonna go up there. So we need v squared to be larger than or equal to r times g, pretty much, for that to happen. Okay, so the statement that is correct is actually C. Okay, and the reason is that if we lose contact, n is 0, therefore v squared must be larger than or equal to r times g for that to happen. Okay, moving on. Question 12. An object is released from rest and oscillates with simple harmonic motion. The maximum kinetic energy is U. The object is stopped and the process is repeated with the initial displacement double. Okay, what is the maximum kinetic energy? So key E, which is U in this case, is 1/2 m omega squared a squared. The new kinetic energy is going to be 1/2 m omega squared times 2a and the whole thing squared, so 4a squared, which is 4u pretty much. So D is the correct answer. Okay, let's continue with question 13. An object of mass 1 kilogram is moving in a straight line at velocity 10 meters per second and collides with an identical object also traveling at 10 meters per second in a straight line. Their initial velocities are perpendicular. The two objects stick together. What is the magnitude in meters per second of the new combined velocity? So we have the first object, let's call it P1, traveling with 10 meters per second. So P1 is 1 kilogram times 10, so 10 kilograms meters per second. And we have another object, which is identical to the first object. So it has the same exact momentum, but in a direction that's perpendicular to the first one, okay? So this is the before situation. And after that, the two objects stick together and they move with some new combined momentum, which we call P. Okay, so one easy way to do this, and by the way, I have a really nice video on momentum and collisions and so on in 2 dimensions. It's very popular. Okay, it is designed for Edexcel, but I suspect it's going to be really useful for OCR students as well. So that's the final momentum. I forgot to write, this is the after the collision situation. So momentum is conserved. So we can think about this as a vector problem, right? So we have P1 and P2, right? And the hypotenuse of, or the resultant momentum, if you will, is the total momentum, okay? So we can simply use Pythagoras theorem because the two momentum before are equal, right? And we can find the magnitude of P. So the magnitude of P is equal to the square root of P1 squared plus P2 squared, which is the square root of 10 squared plus 10 squared, which is 14.14 kilograms meters per second, okay? I ran out of space, so I'm going to use an extra space. So I'm back here. So P is 14.14 kilograms meters per second. That's the magnitude, okay? So what's P though? It's mass, the combined mass, times V, right? And this is 14.14. What's the mass? 2 kilograms now. So V is 14.14 kilograms meters over seconds over 2 kilograms, okay? And this gives us the velocity of the combined object as about 7.1 meters per second, which is option A, okay? You can also do this by taking components. So you need to take conservation of momentum in the x and y directions, and so on. But I felt this one is easier and kind of more intuitive, cool. It looks cooler, maybe. I don't know. Let me know in the comments. And let's move on. Okay, question 14. At the surface of a planet with radius r, the magnitude of the gravitational field strength is g. What is the escape velocity from the surface of the planet? So we can use conservation of energy to do that. So the kinetic energy on the surface of this planet is going to be 1/2 mv squared. Okay, and this to escape, we need this kinetic energy to equal the gravitational potential energy also at the surface of the planet. So this is going to be g m over r. Okay, so m cancels. So we have v squared over 2 is equal to gm over r. But then g, the gravitational field strength at the surface of this planet, is going to be gm over r squared, right? So g times r is equal to gm over r, pretty much, right? So if we combine these two, we find v squared over 2 is equal to gr, which means that v is the square root of gr, which is option 2 times gr, excuse me, forgot the 2. What is a factor of 2 amongst friends? Used to say one of my favorite professors from when I was a PhD student. So yes, mistakes like this, a factor of 2 happens in physics. So option C is the correct one. Okay, finally. 15. Stars rotate around the center of their galaxy. Observations suggest that the stars at the edges of galaxies are moving at much higher velocities than expected. What is the name given to the current explanation of these observations? And this is, of course, dark matter, okay? Because it provides extra gravitational bound and so on and so forth. Okay, question 16. I really like this problem for some reason. So a car of weight 9,300 newtons is moving at speed v. The total resistive force F acting against the motion of the car is given by the formula F equals to kv squared, where k is a constant. The car is allowed to roll from rest down a slope of 5 degrees to the horizontal. The engine of the car is not switched on. The car reaches a maximum speed of 30 meters per second. So question 1 asks to sketch a graph on the axis below to show how the speed of the car changes over time. And then it says add a suitable value to the vertical axis. Okay, I don't know how much detail they need in this problem, but I will analyze it because, okay, the purpose of my videos is to have educational videos. So I don't care about the mark scheme and such. No, I care that my answers are the same as the ones in the mark scheme, but I follow my own kind of reasoning with these papers. Anyway, so what I'm trying to say is that the way I solved it is that I went to the car and used it as a free body diagram to put down all the forces. So we have the reaction from the floor, we have the weight pointing down, and the resistive force F that they mention that points in the opposite direction from the motion. So we need to analyze forces in an axis that is parallel to this ramp. Okay, so let's try to do that. So this angle, that angle over there, is also 5 degrees, and the reason is that to see this you can draw two lines. The first one is to realize that this line is perpendicular to this line, and then this line is perpendicular to this line. So the inscribed angle, which is the 5-degree angle, is the same as that angle. Okay, I hope this makes sense. If it doesn't, ask me. Oops, and I will provide an explanation in the comments. Sorry, I will remove now the lines. Excuse me. Okay, so now we can analyze the weight into a component that is W cosine of 5 degrees. in this sort of tilted, rotated, but it's better to say rotated y-axis. And then in the rotated x-axis, the weight has a component W sine phi. Okay, the engine is switched off, so there is no more force pointing forward. Okay, so the car moves forward, therefore we have W sine 5 degrees minus F, that's the sum of all forces. So this resultant force is equal to mass times the acceleration in that direction. Okay, so the acceleration of this car is W sine 5 minus kv squared over m. Okay, so what does this equation tell us? Let's go to the back and study it. So A is mg sine of 5 degrees minus kv squared over m. Those of you who are going to study engineering or physics, they will learn how to actually integrate this equation to find the velocity. Okay, because you see we have the velocity here, and acceleration is dv over t, so this turns into a nice differential equation that you can solve, but this is beyond the scope of an A-level lesson. So anyway, the point here is that as v increases, okay, A decreases, okay, because as v increases, kv squared increases. So at some point, okay, at some point A becomes equal to 0, and this happens exactly, okay, which happens, okay, exactly when V becomes maximum. Okay, so the car will reach a terminal velocity. Okay, so that's the whole story. Okay, so if we go back and sketch this, okay, we will have a curve. Okay, so the slope of the velocity versus time curve tells you the acceleration. Okay, so this acceleration is going to be the largest at 0, right, at time 0, and then gradually as time increases, the velocity increases. So as t increases, v increases, a decreases. Okay, so I'm trying to say that it's going to look something like this. Okay, so it will eventually reach 30 meters per second. Actually, we should make it touch maybe. So let's see, something like this is going to be the curve. And again, notice that, okay, that's the slope. The slope gives you A. So A is large here, but then it becomes smaller, smaller, and eventually becomes 0. Okay, so I hope this makes sense. Let's move on. Question 2. Explain why the car reaches maximum speed is what we actually already discussed. So, but briefly, as v increases, kv squared increases, and mg sine 5 degrees becomes equal to kv squared. So A becomes 0 and car reaches terminal or maximum velocity. Okay, if this doesn't make sense, ask me in the comments and I will provide more explanations, but let's move on for now. 3. Show that the value of k in the equation f equals kv squared is about 1. So to do that, we will solve kv squared is mg sine 5 degrees, and this equality becomes possible when v is maximum and the maximum velocity is 30 meters per second, as we were told. So we can just solve for k. So k is mg sine of 5 degrees, okay, over v squared, right? Okay, so we have 930 newtons. Okay, newtons. That's the weight times 0.09, which is sine of 5. Okay, over 30 squared meter squared seconds squared. Okay, so this evaluates to 0.1, and then I'm gonna analyze expanding newtons into base units. So newtons are kilograms meters per second squared, and then we have to multiply by seconds squared over meters squared. Seconds cancel, meters cancel. So sorry, actually this is 0.9, excuse me. Okay, so the final value for K is approximately 1 as asked, and the units are kilograms per meter. Okay, I hope this makes sense. Let's move on. Okay, B, the car is now moving along a straight level track. The engine of the car delivers a maximum power of 75 kilowatts. Calculate the maximum speed of the car. Okay, I'm gonna. Do I have enough? I don't have enough space, so I'm gonna do part B in the back. So here, so this is the horizontal road, and this is the car. Now we have two forces. We have the force from the engine. Okay, and this force is going to be equal to the power provided over the velocity. Okay, and we still have the resistive forces. So F equals to kV squared. Okay, so again in this scenario the car will reach a terminal velocity, so the motion is forward. So we take if we use Newton's second law, we have P over V minus kV squared is equal to ma, but the question asks calculate the maximum speed. Okay, so at V max, the acceleration is 0. So we can set these things equal to each other. So we have P over V is equal to kV squared, or V cubed is P over K. So V is the third root of P over K. Okay, is that correct? Yes. Okay. So we have the cubic root of 75,000 watts, and 1 watt is, I'm going to write it as joules per second. Okay, and the units are also under the square root. By the way, I forgot to mention, because this is the first video on OCR, the way I solve problems is that I try to reach an algebraic expression that gives me the quantity I want to calculate. So in this case, V. Okay, so that's the algebraic expression in the red box. And then when I plug in numbers, I plug in all the numerical values to the left and all the units to the right. Okay, so I can work with them independently. Okay, for K, we're going to use the 0.9, which was the actual value we used. And the units for that is kilograms per meter. Okay, so this evaluates to 43.68. And then the units are a little bit tricky. So I'm going to expand the joule. The joule is kilograms meter squared over second squared. And then we have another leftover seconds from before. And then times meters over kilograms. And this whole thing is to the 1/3. Don't forget that. So kilograms cancels. And we have meters cubed over seconds cubed to the 1/3. So eventually we get meters per second pretty much. So 43.68 meters per second. Okay, which is the answer. Okay. C, changes are made to the engine of the car so that it can produce double the original maximum power. Okay, so someone has a lot of money to spend, I guess. But anyway, explain why the maximum speed of the modified car is not double. So at V maximum, okay, V is proportional, we just proved that, to the power to the 1/3, right? So if P is doubled, okay, V only increases by 2 to the 1/3, which is equal to 1.26. Okay, so the increase is only 26%. Okay, so the modification that this random dude made to his car Didn't get him as far as he wanted, probably, but it's his problem, not ours. We solved ours, actually, so we don't care. Let's move on to the next question. Okay, question 17. State Newton's second law of motion. So the resultant force, okay, on an object. I feel I'm gonna run out of space, so I'm gonna use a new page, okay? So the net force on an object is proportional to its rate of change of momentum. So is proportional to its rate of change of momentum, okay, and acts in the direction of that change, and acts in the direction of that change. And in mathematical form, the sum of all forces is mass times acceleration, or the change, the rate of change in momentum, delta p over delta t. Okay, so that's a more than enough answer, I hope. I mean, to get it's just 1 mark. Okay. B. A model of an aircraft is being tested in a wind tunnel. That's exciting. It's exciting stuff, by the way. People who are interested into aerodynamics should study, should look into programs in the United States. So when I was a PhD student in the US in my university, it was Notre Dame. Okay, I can mention it. They were building a tunnel to test for wind turbines. Okay, so it's really exciting physics, but okay, it's more on the engineering side of physics because you do constructions and stuff like that with this kind of work, but it's really interesting. So anyway, a model of an aircraft is being tested in a wind tunnel. The model is fixed in position by support, and air is blown horizontally towards it by fans. In 1 second, 35 kilograms of air moving at 50 meters per second hits the model. So we have the duration of this change, okay, the volume of air and the velocity, okay. After flowing through around the model, the airflow is diverted downwards at an angle of 30 degrees to the horizontal. The speed of the diverted airflow remains at 50 meters per second. So question I asks to calculate the horizontal and vertical components of the velocity of the diverted airflow. So let me go here and actually draw the situation. So I'm gonna try to draw a toy plane. So I don't know, something like this maybe. Okay, this is an aeroplane from the time of Leonardo da Vinci, maybe. Okay, so you have the airflow. Actually, let's use blue for air. Okay, so you have the air coming in at 50 meters per second, and then once it passes through the wings, I guess it bends downward. Okay, and this angle is 30 degrees to the horizontal. Okay, so that's the situation. So if you want to draw it as a vector, so you have the magnitude as 50 meters per second. Okay, and that's the 30-degree angle. Okay, so Vy is going to be 50 times sine of 30 meters per second. Okay, and Vx is going to be 50 cosine of 30 degrees meters per second. And the reason why it's cosine, it's because Vx, as I say, touches the angle, meaning that, okay, so this component, the x component of the velocity touches the angle, whereas the y component does not touch the angle. So the one that does not touch it is the sine. That's how I remember it. So it's silly, but I don't know, it helps. So let's come back here and write down Vx is going to be, if you evaluate the cosine, you get 43.3 meters per second. And for Vy, you get 25 meters per second. Technically, it's a minus sign because it points downwards. But okay, I mean, it's not needed is my guess. Okay. 2, explain how the airflow around the model produces a force on the model. By the way, there are two schools of thoughts that I always forget. I think there is the Newton's school of thought and the Bernoulli's school of thought about why airplanes fly. You can look it up, but it's a fierce competition between the two explanations. Both are valid. I think the one says that a lift occurs because of the difference in pressure that occurs between the upper part of the plane and the lower part of the plane, and I think that's Bernoulli's explanation. And then it's not. I mean, Bernoulli was not alive when the airplane was manufactured. It's just his principle, I think. Okay, so they use the principle to explain it. And the other argument is Newton's argument, and I guess because this is a British exam, this is what they push towards. Okay, the Newton's explanation, which says that it's the change in momentum of the air particles that causes the lift, but you can check it for yourselves. So anyway, it's an interesting trivia. Okay, I'm gonna use extra space again. So part 2 is gonna be treated here. So the air, we can write that the air arrives horizontally, okay, but it's deflected downward, okay, after flowing around the model, okay. The momentum of the air, okay, has changed, okay, as we add a downward component, okay. I hope this is clear. If we come here, you see that initially the momentum is horizontal, but then it bends downwards, so the momentum changes, okay, because of the change in direction, okay. So by Newton's third law, so you see this is, I'm gonna write this as N3, that's Newton's third law. So this is Newton's explanation why planes fly. Again, Sir Isaac Newton was long gone when the airplane was discovered, I mean, invented, whatever the correct wording would be. I think Newton lived, when did he live? In the 16th century? Let me know in the comments, but yeah, he was definitely long gone. So by Newton's third law, if the model exerts a downward force on the air, okay, comma, the air exerts an equal and opposite upward force on the model. Okay, so this creates a lift. Okay, but we are not done yet. There's a third part in this question. So part 3, calculate the vertical lift force acting on the model due to the airflow around it. So what am I doing? Sorry. So in 1 second, okay, 35 kilograms move with Vy equals to 25 meters per second downward. Okay, so the force is the change in momentum with respect to time. So the momentum is 35 kilograms times 25 meters per second for the y component. That's the final momentum minus the initial momentum in the y direction, which is 0, because remember, this is the picture. Initially, we only have a horizontal component and no vertical component, okay? So 0 is the initial momentum in the y direction. And the duration is 1 second, okay? And the units are kilograms, meters per second, and then we get another second in the denominator, so we get newtons. So this is 875 newtons, okay? and this evaluates to newtons. And this was question 17. I hope it makes sense. Let's move on. Okay, 18. Mats made from rubber are often used in laboratories where heavy objects might be dropped. A rubber core is tested to determine the material's mechanical characteristics. The core is suspended from a ceiling, this is question A, and masses can be attached to the free end. The apparatus is set up as shown in figure 18.1. Okay, so you have the core made from rubber band attached from the ceiling, and we measure that height h as we add masses. Okay, so masses are added and the height h of the base of the bottom mass from the floor is measured. The extension of the cord is x when the tension in the cord is F. After 6 masses have been added, they are removed one at a time and h measured each time. Okay, the table shows the data collected. Question 1 says, complete the final column of the table. I think they should have said something like the missing data, the missing datum, whatever, something like that. But they say the final column, so that threw me off. But they actually mention, mean that value over there. Okay, so this is the loading phase, so they keep adding loads. So this value here, I mean, you see that x is 0 when there are no masses, and then x is 0.2 because the h reduces to 1.6 from 1.8. So all you have to do is to subtract 1.8 minus 0.81 to find that this is 0.99 pretty much. Okay, I hope this makes sense. If it doesn't, ask me in the comments, but it's pretty simple, I guess. So this point is 0.24 because the height is now 1.56, but the height when the force is 0 is 1.8 and so on. So just subtract and find it. Okay, let's move on. 2. Plot the data point for 6 newtons on the graph above. The other points have been plotted. Draw and label 2 curves and show the loading and unloading of the cord. Okay, so the missing point is, as we found, x is 0.99 meters, so we can put it there. I think it's safe. Okay, it should be a little bit to the left, so maybe there, somewhere there. But okay, I mean, we can put it, okay, it's fine. Okay, now let's draw the 2 curves. I'm gonna use a different color. So with red, we're gonna do the loading curve. Okay, by the way, notice that so they keep loading, so they keep adding masses until we reach 6 newtons, and then they start removing masses. So we have 5, 4, 3, 2, 1. And then notice that when all the loads are removed, x is 0.05 meters, which we see there. Okay, so that point is part of the unloading curve, and it's because this cord does not follow Hooke's law. Okay, it's a rubber band. Okay, there is a leftover plastic deformation in it. This is what this information over there tells you. Okay, so let's use red for the loading. So we have to connect this point with this point and this point. I'm hoping I'm doing a good job. And okay, that's the loading curve. So let's write loading. And then we unload it. Let's use blue. So we start from the same point we stopped earlier. So we go through the points. Okay, and we connect it. And that's the unloading. Okay, I think it's good. So let's move on. Part 3, discuss whether Hooke's law can be applied to the cord. We already said it cannot. So I want to write a few things though. So I'm gonna move to a clean page as usual. So this part 3. Okay, so the first thing we can write is that Hooke's law requires F proportional to x, okay? So a straight line through the origin. Okay, so this is clearly not what we see here. So the loading curve, okay, is not straight. Okay, so f is not proportional to x. Okay, additionally, okay, when fully unloaded, okay, x is 0.05 meters and not 0, okay, which means the cord does not return to its original position. Okay, and it has plastic deformation. So Hooke's law cannot be applied. Okay, let's move on. Part 4, and then there is a part 1 in part 4 in question part A. I don't know, it's a little bit confusing. So anyway, state the name of the derived SI unit of this area. Okay, so area is force times distance, so newtons times meters, which is the joule. Okay, so that's energy. Okay, part 2, explain the significance of this area to the planned use of the rubber. Okay, I guess I mean the area between the two curves, because part 2 of question 4 is related to that. So I'm gonna use the extra space. So this is 4, oops, that's 6, not 4. So 4 and then 2. So, okay, let's answer it here. So the area between the two curves, okay, is the energy dissipated, okay, as thermal energy, okay, inside the rubber, okay, during one full loading unloading session, or maybe cycle is better. Okay, let's create another clean page. So this energy is not returned to a falling object. Okay, so the object bounces with less kinetic energy. Okay, a larger area, okay, means more energy is absorbed, resulting in smaller forces on both the object and the floor. Okay, and this reduces the risk of damage. Okay, so this is why this rubber is good to be used for falling objects. Okay. Okay, this was done. Part B. An alternative arrangement for the experiment is to use a pulley as shown in figure 18.2. The arrangement makes it possible to cover a larger range of extensions. Okay, describe two factors that would affect the accuracy of the results obtained using this alternative arrangement. So the pulley introduces friction. Okay, so the actual tension is less. So the actual tension is now less than the weight of the masses. Okay, uh, so yeah, I mean that introduces an error. Then on the flip side, greater length, okay, used will reduce the percentage uncertainty in H, okay, which is equal to the absolute uncertainty in H over H, right? And then we can, so this is point 1, let's remove that, so this is point 2, and we can write another point. So larger range in H makes use of a ruler harder, okay, introducing systematic errors in H. Okay, so I think we're done with this problem. Let's move on. Okay, 19, it's a start problem, which is, I mean, in Excel, these are long writing problems, so I guess it's the same idea. Describe how to determine the wavelength lambda of a monochromatic laser pointer using a diffraction grating. As part of your answer, explain how to analyze the measurements collected using a graphical method, improve the accuracy of the measurements taken. You are given the number of lines per millimeter for the diffraction grating. So the setup is something like this. So this will be the laser, and then we will have the diffraction grating, I guess. Okay, and this is the laser beam. Okay, and we will have a screen. Okay, and we will have a central maximum, and then we will have other maxima on both sides. Okay, so this will be the distance d from the grating to the screen. Okay, and this will be y1, and this will also be y1. Okay, it's the distance from the central maximum to the first order maximum, and then this will be y2, which is the second order maximum, and so on. Okay, so let's write the setup. Okay, shine the laser through the diffraction grating. Okay, onto a screen, okay, or wall. Okay, ensure the grating is perpendicular to the beam. Okay, identify the central n equals 0 max and the other maxima of orders n equals 1, 2, 3. Usually 2 are visible. It depends on the wavelength of the laser. Okay, measure d, the distance from the grating to the screen. Measure yns. Okay, and then find the tangent of theta, which is equal to yn over d. Okay, now I will need, yeah, we have extra space here. So graphical analysis now. Okay, graphical analysis is what comes next. Okay, once we have all these measurements, we have to first convert lines per millimeters to d, which is 1 over lines per millimeter. Okay, times 1000. No, we don't have that. We don't need that. Okay, so yeah, okay. So the next one is to apply d sine of theta is equal to n lambda. So sine theta is proportional to n. Then plot sine theta versus n, which is of the form y equals mx. Okay, with y, actually plot d sine theta versus n. So y is going to be d sine theta, and your x is going to be n. So the gradient of best fit line is lambda. Okay, and to improve accuracy, okay, use a large room. So larger d reduces the percentage uncertainty in d. Okay, sorry, in y, not d. Okay, it's going to be easier to measure y if d is large. Okay, measure 2y and divide. Okay, instead of measuring just y1, measure the whole thing and then divide by 2. Okay, use dark room so that the maxima are visible. Excuse me. Use a grading with a large number of lines per millimeter. So d is smaller. Okay. This will spread maxima further apart. Okay, so this was question 19. It's kind of long. These are not my favorite types of questions, to be honest, but you have to do them. So let's move on to question 20. Okay, 20A, part 1. Define the internal energy of an ideal gas. So the sum of the randomly distributed kinetic energy of all particles in the gas. Okay. Part 2, use the formula below to show that the average kinetic energy of a particle of an ideal gas is directly proportional to the absolute temperature of the gas. So we can set these to equal to each other. So nkt is 1/3 nmc squared average. So n cancels, and we can introduce a factor of 1/2 in both sides. So 1/2 mc average squared is 3/2 kt. Okay. B. The velocities of 4 gas particles at 290 degrees Celsius are given below in meters per second. Show that the root mean squared RMS speed of the sample is about 430. Okay, so we can sum this up. So let me think. So VRMS is the square root of 310 squared plus 370 squared plus 440 squared plus 550 squared under the square root. So this is 430. So 426.9 which is about 430 meters per second. Okay, 2. Calculate the molar mass of the gas, assuming an absolute temperature of 290 Kelvin and RMS speed of 430. Okay, so we will use what we just proved. So, this formula, so we're going to use it here. So, mass is 3 kT over c squared. Okay, so this is going to be 3 times 1.38 times 10 to the negative 23 joules per Kelvin, and then times the temperature 290, and that's Kelvin, and then velocity squared 430 squared, and then meters squared, second squared, so Kelvins cancel, and joules are kilograms. I will explain in a moment. So we get 6.49 times 10 to the negative 26 kilograms. Okay, and this is because the joule again is kilograms meter squared over second squared. Okay, but we are asked for the molar mass. So the molar mass m is the mass of one molecule times Avogadro's number. So 6.49 times 10 to the negative 26 times 6.02 times 10 to the 23, and then kilograms per mole. And I will need extra space, I'm sorry. Okay, so the molar mass is 0.039 kilograms per mole. Okay, I hope this makes sense. Let's move on. Part C. Spherical filament lamps, spherical filament lamps are manufactured by a process where they are filled with a gas at 290 kelvins and low pressure. When the filament lamp is switched on, the filament reaches a constant temperature of 2400 kelvins. At this temperature, the pressure inside the filament lamp is 120 kilopascals. Question I. Explain in terms of energy transfers why the temperature of the filament does not increase beyond 2400 kelvins. You are not expected to refer to the electrical characteristics of the filament lamp. Okay, I'm going to go to the back so I have space. So this is C1. Okay, so when the lamp is switched on, okay, electrical energy is transferred to thermal, which is internal, okay, to thermal energy of the filament, okay, raising its temperature. Okay, now as T increases, okay, for the filament, okay, it transfers energy to the gas inside the lamp, inside the lamp by conduction, and to the surroundings by radiation. Okay, at 2400 Kelvin, okay, the rate at which the filament loses energy to the surroundings, okay, exactly equals the rate at which energy is supplied to it. Okay, so net energy transfer becomes 0. Okay, hence T becomes constant. Okay, so electrical energy is transferred to thermal energy in the filament. As the temperature of the filament increases, the energy is transferred to the gas. Okay, And then once we reach 2400 kelvins, the rate at which the filament loses energy to the surroundings is exactly equal to the energy at which energy is supplied to it. So there is no net energy transfer anymore. So the temperature remains constant. Okay. So let's move on to part 2. So in part 2, we have to calculate the pressure of the gas within the filament lamp during manufacture. So we have the initial pressure when it's manufactured times the volume of the lamp is going to be equal to the number of particles times K times the initial temperature, okay? And then when it's switched on, final pressure times volume is going to be N times K times the final temperature. So if we divide these two, we get these really nice cancellations, and we can solve for Pi. So Pi is Ti over Tf times Pf, but everything is given to us actually. So during manufacture, we have 290 kelvins, the final temperature is 2400, and the final pressure is 120 kilopascals. And if we evaluate this, we get 14.5 kilopascals, which is the answer. So we're done with question 20. Let's move on to question 21. Okay, this question is about analyzing the electromagnetic radiation from the star Nu Persei in the Milky Way galaxy. To be honest, I never heard of this star. If you did, let me know in the comments. So figure 21.1 shows the relative intensities of different wavelengths of electromagnetic radiation from Nu Persei. The surface temperature of the sun is 5800 Kelvin, and its wavelength at which maximum intensity is emitted is 500 nanometers. The luminosity of Nu Persei is 2.3 times 10 to the 29 watts. Use figure 21.1 to show that the surface temperature of Nu Persei is about 6300 Kelvin. Okay. So from Wien's law, we know that lambda times T is a constant, right? So we can exploit this and write that lambda sun, the peak wavelength of the sun, times the temperature of the sun, and we are given both information here, okay, for the sun, is going to be equal to the lambda, let's call it nu times T of Nu Persei, okay? So if we solve for T nu, T nu, we get lambda sun over lambda nu times T sun. But we are missing lambda of Nu Persei, but we can use the graph. So something like that. So I used lambda nu equal to 450 nanometers. But if you go a little bit to the right or to the left, I think they're going to be fine with that. I mean, in terms of the mark scheme. So this becomes equal to 500 for the sun over 450 times 5800. So we find that the temperature of Nu Persei is 6444.4 kelvins. Okay. The second question is to estimate the radius of Nu Persei. So we're going to use Stefan Boltzmann's law, sigma times 4 pi r squared times t to the fourth is equal to the luminosity. So we are searching for the radius. So r squared is equal to the luminosity over sigma 4 pi and then t to the fourth. I'm going to use extra space. So we have r squared is 2.3, okay, 2.3 times 10 to the 29, and then we have watts, right? And then sigma, okay, let's write the 4 pi first, and then sigma is 5.67 times 10 to the minus 8, and the units are watts over meters squared, and then kelvins to the fourth, and then T to the fourth, so 6444.4 to the fourth. And then we have kelvins to the fourth. So watts cancel, kelvins cancel, and we find 1.87 times 10 to the 20 meters squared. So if we take the square root, we find that R is 1.37 times 10 to the 10 meters. Okay, moving on. B, electromagnetic radiation is collected from New Percy by a sensor with an efficiency of 11% and cross-sectional area of 1 times 10 to the minus 4 square meters. The radiant power collected by the sensor is 7 times 10 to the negative 15 watts. Show that the radiant power per unit area arriving at the sensor is about 6 times 10 to the minus 10 watts per meters squared. Okay, so basically you can think about this, that that the efficiency times the radiant power, which we will call P naught, is equal to P, right? So P naught, which we try to find, is the P over the efficiency, and the P collected is 7 times 10 to the negative 15 over 0.11, which yields 6.36 times 10 to the negative 14 watts, which, let me think, which is that's the radiant power in total, okay? And then the intensity received is I naught equals to P naught over the area given, so 6.36 times 10 to the negative 14 watts over 1 times 10 to the negative 4 meters squared, which yields 6.36 times 10 to the negative 10 watts per meter squared, which is very close to what they are asking. Okay, so the trick here is to recognize that by dividing with the efficiency, we find the total power. Okay, part 2. By the time the electromagnetic radiation from New Percy reaches Earth, the radiation from New Percy is evenly distributed over a spherical area with radius equal to the distance between New Percy and Earth. Calculate the distance of New Percy from Earth in light years. So this I naught is equal to the luminosity of New Percy over 4 pi d squared, okay? So d squared is L over 4 pi I, which is equal to 2.3 times 10 to the 39 watts. And then in the denominator we have 4 pi times I naught, right, which we calculated earlier. So 6.36 times 10 to the negative 10 watts, and then meter squared. So this cancels, and we get d squared equal to 2.88 times 10 to the 37 meters squared, which means that d is 5.36 times 10 to the 18 meters. And if we divide, because they ask for light years, if we divide by 9.5 times 10 to the 15 meters, we can convert to light years, and we find 564.7 light years. Okay, which is the answer. So let's move on to part C. Okay, part C, the luminosity of New Percy was estimated using the temperature of New Percy and the Hertzsprung-Russell HR diagram in 21.2. L is the luminosity of a star, and L with that circle is the luminosity of the sun. The temperature data from earlier in this question is repeated in the table below. Comment on the uncertainty in your value calculated in B2 of the distance of New Percy from Earth. You may write on the diagram as part of your answer. Okay, so first of all, looking at the diagram, okay, at 6300 kelvins, the main sequence spans a range, a range of luminosities. And what I mean is that if we draw a line from 630, we see that it can be, the luminosity can be the same as the one of the sun, or one time, okay, so this will be one, okay, but it's a log scale, so the luminosities here span a range from the luminosity of the sun to 10 times the luminosity of the sun. So a range of luminosities from L of the sun to 10L of the sun. Okay, so that introduces an uncertainty. Okay, let's use a clean page again. Okay, so the L used could be anywhere in that range. Okay, so there is an uncertainty in L. Okay, so since the distance is proportional to the square root of L, okay, an uncertainty of 10L of the sun, okay, leads to a factor of 3.16 uncertainty in distance. Okay, so the percentage uncertainty in the distance is proportional to L over 2. So, and this is because when we calculate percentage uncertainties of powers, we multiply the percentage uncertainty of the measurement itself with that power. Okay, and I have a video on that, by the way. I mean, in case you want to check my channel. So, on top of everything, okay, New Percy might not even be in the main sequence. Might not even be in the main sequence. Okay, so that's a pretty good answer. This is a good time to stop and move on to the next problem, which is 22. Okay, 22, a satellite in a geostationary orbit around the Earth appears to remain at the same point in the sky when viewed from the ground. State one condition required for an orbit to be geostationary. So we need equatorial orbits, okay, with a period of 24 hours. Okay. What's wrong with me today? My handwriting is horrible, guys. For those of you who are watching my videos for the first time, I do my best, but it always slips. Okay, 2. Calculate the orbital radius of the geostationary satellite. The mass of the Earth is 6 times 10 to the 24 kilograms. Okay, so so the gravitational force is G times the mass of the Earth times the mass of the satellite over r squared, and this is equal to the centripetal force, excuse me, which is equal to the mass of the orbit, of the satellite times omega squared times r. So the mass of the satellite drops out. Okay, so r cubed becomes equal to G. Wait, I skipped a step. So gm over r squared is 4 pi squared r over t squared. So r cubed is equal, oops, we don't need that yet, is equal to g times m times t squared over 4 pi squared, and then I'm going to go to the back and perform the calculation. So r cubed is 6.67 times 10 to the negative 11 times 6 times 10 to the 24 times 24 hours times 60 minutes times 60 seconds squared over 4 pi squared. And then the units are from G, we have newtons, let me think, times meter squared, kilograms to the minus 2, and then times kilograms from the mass of the earth, and then times seconds squared. Okay, so this evaluates to 7.57 times 10 to the 22. And then let's see what kind of cancellations do we have. If we expand the Newton, we get kilograms meters over second squared times meters squared times kilograms to the minus 2 times kilograms times second squared. So seconds drop out, the kilograms cancel, and we are left with meters to the cubed, which is okay. So r is the cube root of all that, so 4.23 times 10 to the 7 meters. Okay, part B, a satellite of mass m is in circular orbit around a planet of mass capital M. The radius of the orbit from the center of the planet is r. The gravitational potential Vg at a point distance r from the center of the planet is given by the equation Vg equals to minus g times m over r. Question I, by considering the cause of the centripetal force on the satellite, show that the kinetic energy of the satellite is equal to half the magnitude of its gravitational potential energy. So, okay, so first of all, we have gmm over r squared equal to mv squared over r, okay, which is the same thing we wrote earlier, but with the velocity now, okay? So these are drops and the mass drops. So v squared is g times m over r. Okay, now the kinetic energy of the satellite is 1/2 mv squared. So 1/2 gmm over r. Okay, now the magnitude of let's call it u gravitational, okay, is equal to the mass of the satellite times the magnitude of the gravitational potential Vg, okay? So it's equal to mass times gm over r. So immediately see that the kinetic energy is actually 1/2 times the magnitude of the gravitational potential energy, okay? So that's the proof. Let's move on. 2. A tiny satellite of mass 1 kilogram is to be launched from rest from the surface of the Earth into a low Earth orbit. The gravitational potential at any point in this orbit is minus 56 megajoules per kilogram. The value of the gravitational potential at the Earth's surface is minus 63 megajoules per kilogram. Show that the satellite must gain more than 30 megajoules of total energy to achieve and remain in orbit. So we will need, let's calculate the energy. So we will need delta U equal to m times delta V, which is going to be 1 kilogram for the satellite, times minus 56 minus the minus 63, okay, megajoules per kilogram. So the kilograms drop out. So we will need 7 megajoules per kilogram. I mean, in terms of gaining gravitational potential energy. And we will also need a KE, a kinetic energy, which is going to be equal to the potential energy at that orbit over 2. Okay, so what will be the gravitational potential energy at that orbit is going to be the absolute value of minus 56 over 2. Actually, let me use a clean page because everything is crammed there. So again, let's summarize. We will need 7 megajoules per kilogram from the GPE, okay, and and the kinetic energy equal to 28 megajoules for the key E of the satellite in its orbit. Okay, so in total we need 28 plus 7 equal to 35 megajoules of energy, which is larger than 30 megajoules as we were told. So C, it's a star problem again, so 6 marks. Large satellites are often launched by rockets from sites near the equator. The rotation of the Earth increases the initial kinetic energy of the rocket and satellite. A new strategy is to launch with using a smaller rocket from a high-flying aircraft. Using the information in B2 and the data below, evaluate the advantages and limitations of this strategy. Use calculations to support your evaluation. Okay, the rotational speed at the equator is 460 meters per second. So the kinetic energy from that rotation is 1/2 times 1 kilogram times 460 squared, or 105.8 kilojoules. Okay, that's one form of energy. And related to the rotational speed. Now let's analyze this data over here. So the kinetic energy of the aircraft is 1/2. So just by being in the aircraft, the satellite gains 1/2 times 1 kilograms times 230 squared, or 26.5 kilojoules just by being in the aircraft. And there is also a GPE gain, okay, from the aircraft, which is mgh, so 1 times 9.81 times 10,000 meters, which evaluates to 98.1 kilojoules. Okay, so the total for aircraft is 98.1 plus 26.5, or 124.6 kilojoules are gained by the satellite just by being in that aeroplane. Okay, now let's see. Okay, let's use a clean page. Okay, so but the total energy to reach and stay in orbit is 35,000 kilojoules. Okay, so from the rotation, the gain is just 105.8 over 35,000 times 100. The gain is 0.3% for the rotation. And with the aircraft, the gain is 124.6 over 35,000 times 100. The gain is 0.36%. Okay, now let's talk about advantages and limitations. So advantages, okay, aircraft provides 124.6 kilojoules, which is slightly more than 105.8 kilojoules provided by just the rotation of the planet. Okay. And lest I forget, uh, the European Space Agency actually has its launching station in French Guiana, okay, which is in South America near the equator, okay, and they do the launching of the rockets from there for this reason, okay. So in case you don't know, and that's considered French soil, so it's considered part of the European Union, if I'm not mistaken. I'm not entirely sure, and this touches on political issues that I don't really want to discuss in my channel, but this is something to know. So look it up. So the aircraft. So the advantage of the aircraft is that the aircraft can operate from anywhere. Okay. So no need for launching station near the equator. Okay, so the two advantages is that we gain some energy from the airplane, which is slightly more than the one provided by the rotation. And most of all, you can do this from anywhere on the planet. You don't need to be near the equator, and you don't need a launching station. Now, as for the limitations, okay, so energy savings are minute. I mean, in the order of 0.4%. It's not much. I mean, it would be great if it was 20% savings, right? Then also the aircraft speed is only 230 meters per second. So kinetic energy gains are small. Okay. And the other limitation is that this method can be used with only light microsatellites. So when I worked in a liberal arts college in the United States, I had a colleague who was interested in microsatellites, and I first became familiar with them. So these are literally, I mean, they exist. They are 1 kilogram, and you put them in geostationary orbits, and they are used to collect data for whatever you need to collect data. I don't know, weather, I don't know, maybe spying, I don't know. But it's fun that these things are possible nowadays. So we're living in exciting times, at least in terms of technology. So let's move on to the next question, which is the last question in this test. Okay, question 23. The diagram shows some of the energy levels of the electron in a hydrogen atom. An electron moves from energy level X to energy level Y. Show that the wavelength of the photon produced is about 410 nanometers. Okay, so the change in energy is equal to h times the frequency, which is equal to h times c over lambda. So lambda is hc over delta E. So I don't have enough space as usual, so let's move back here. So lambda is 6.63 times 10 to the negative 34 times 3 times 10 to the 8, and the units are joules times seconds and then meters per second, and then we have to divide by the change, which is equal to 4.84 times 10 to the negative 19 joules. So everything cancels, and we get 410.95 nanometers, which is about 410 nanometers. Okay. B. The light from the stars in a distant galaxy is analyzed on the Earth using a diffraction grating. Dark lines are observed in the spectrum. An astronomer concludes that the dark line at the wavelength 432 nanometers corresponds to the electron transition between X and Y. Part 1, explain the origin of the dark lines. I'm going to go to the back. So light from stars, okay, passes through, okay, through cooler gas in the stellar atmosphere, okay. That's the first thing. So electrons in these gas atoms, so in these gas atoms absorb photons whose energy exactly matches the gap between energy levels, okay, jumping to higher levels, okay. So these specific wavelengths are removed from the continuous spectrum, okay, leaving dark absorption lines. Okay, now let's go to part 2. Calculate the recession velocity v of the galaxy. So we are told that we see the dark line at 432 nanometers, whereas the wavelength is actually 410.95 nanometers. So we can use delta lambda over lambda is equal to v over c. So v is c times delta lambda over lambda. And this delta lambda, notice that we go from 410 to 432, okay? So we go to larger wavelengths, which means that we have a redshift, okay? So it moves away from us, this galaxy, okay? So c times 432 minus 410.95 over the wavelength at the Earth, okay? These yields, we need to go to the back, okay, over here. So v is 0.0512 times the speed of light, which is 1.54 times 10 to the 7 meters per second, which is the final answer. And there is one more question, part 3. State the name of the theory that is supported by evidence from the measurement of the recession velocities of galaxies in the universe. So the Big Bang theory, or we can also call it the Hubble's law. Okay, and no, I really don't like Big Bang's theory. It feels childish to me. It's very stereotypical. I don't know. It's annoying. I mean, if you're an actual physicist, it's annoying, I guess. So I don't know what you think about the show. But hey, if the show is watching me, guys, you can sponsor me or something. So anyway, this is my first attempt on an OCR paper. I liked it. It's, I mean, I needed a change anyway. But okay, I'm posting this in the summertime, so sadly, it's probably not gonna get any views. But do let me know what you think about it. Again, sadly, this channel is not viable yet, so I don't know for how long I will keep doing this, but we'll see. And yeah, I mean, most of the people who watch these videos are not subscribed for some reason. Actually, 92% of the people who watches my videos are not subscribers, so that's really, really sad. So guys, please like, subscribe, share with your friends, let me know your thoughts. And if you want to support my channel, and I had my first supporter, by the way, a few weeks ago. It made me really happy. I mean, okay, it was just €5, but it's a nice gesture. Okay, I mean, I need to find ways to make this channel viable. So thank you to the viewer who actually supported me, and it will be great if I find ways to support this channel and make it into something bigger. So anyway, this is it. See you in the next video, guys. Bye.